So we're Western Trillium Hyperloop. We'll be talking about our Hyperloop electrical system that we designed today. Just a little bit of overview about our team. By the way, my name is Yemini. I am the club president for this year. So I'll just be going over what our team has worked on. So basically, Trillium Hyperloop was founded in 2020, and it was made with the goal of bringing unique strategies to put together a unique Hyperloop system. We've made great progress in the areas of design and simulation, as well as prototype in many of the key areas. And currently we're working on efficient redesign and testing methods for the subsystems and for the full-scale pod model. For the electrical system, this includes the linear induction motor, the inverter and battery system, as well as the software system that includes sensors and measurements. So the software system that we use is OpenLink software, and that's designed by the team in-house. The main issue with testing an electrical subsystem is that we don't have track access, and electrical systems do require additional testing systems after simulations to show real-world conditions. Our solution for this was the flywheel electrical system. So this is a scaled down version of the electrical subsystem. It would be within a caged mechanism, includes a rotating disc, as well as linear induction motor, braking, and any other electrical components that would be necessary to simulate the movement of a flywheel. This is done so that we can measure power requirements as well as speed and temperature sensing, and so that we're also able to find the speeds at which the system is able to achieve using factors that would arise from system interactions, just like you would see in a real-world pod. So I'll pass it on to my team lead, Kiana, who's going to talk a little bit about the linear induction motor that we use for electrical system.
Hi, everyone. Yeah, so my name is Kiana, and I am the linear induction motor team lead for this year. So our focus for the linear induction motor subteam is to continue integrating and advancing our current electric motor technology. And this is validated through testing on our flywheel system, as Yamini just mentioned. And our goals are for optimizing the efficiency and performance of the linear induction motor to achieve our set goals for velocity and acceleration of the pod, which are 28 meters per second and 2.81 meters per second squared, respectively. So to achieve these goals, our focus has been on refining the three-phase current that's drawn by the limb, as this operates the motor and generates flux within the coils of the stator. So ultimately, the induced current interacts with the flux to produce a linear force or thrust. So specifically this year, the development has been focused on the double-sided limb as opposed to the single-sided option due to the fact that there is additional stability provided perpendicular to the motion of the pod, as well as a reduction in flux losses. So in terms of the overall construction for the limb this year, the focus has been on the development of the stator, which consists of laminated sheets of silicon steel with slots cut into it to house the coils. So this material was selected as it has high permeability, which reduces the effects of eddy currents and hysteresis. So the coils will produce a rotating magnetic field, which will propel the Hyperloop pod. And ultimately, the stator will be the moving portion of the linear induction motor and will be attached to the pod itself. And the coils will be connected to the three-phase current that is produced from the inverter. So as the linear induction motor is dependent on the inverter system for adequate acceleration, deceleration, and speed, I'll now turn it over to my teammate Wajma to discuss the importance of the inverter system.
Hi everyone, my name is Wajma and I'm the inverter lead this year, and I'll be talking about the inverter subsystem of the pod. So this is the first year we're extensively researching, designing, and implementing a unique inverter system to provide an appropriate voltage and frequency to the linear induction motor. So our team's main three goals this year are to provide smooth acceleration, deceleration, and reach the desired maximum speed of the pod, to minimize mechanical and thermal stresses while driving the linear induction motor, where the team will look more into the trade-off between decreasing the switching frequency of the transistor and the resulting harmonics and torsional vibration of the system. And our final goal is to provide protection to the linear induction motor and the entire system by implementing safety switches and appropriate power sensors. So as was mentioned earlier, the team goal for this year is to design and test the electrical subsystems on the flywheel as a proof of concept to demonstrate the validity of the electrical subsystems. So therefore, the team came up with new scaled down specifications. So the maximum speed of 28 meters per second was scaled down to 5.55 meters per second for the flywheel proof of concept. Acceleration of 2.81 meters per second squared in 10 seconds was scaled down to 0.69 meters per second squared in 8 seconds for the flywheel. And the acceleration of negative 5.61 meters per second squared in 5 seconds was scaled down to negative 0.28 meters per second squared in 20 seconds. And finally, maximum stator frequency 58.4 hertz was scaled down to 34.7 hertz for the flywheel proof of concept. So the main role of the inverter subsystem is to convert direct current voltage into three-phase alternating current voltage. And in order to achieve this, the team must consider power handling and dissipation, like static power dissipation due to leakage of current when the circuit is idle, dynamic power dissipation when the circuit is switching, and short power dissipation during transistor switching. The team will implement pulse width modulation for switching the transistors in two methods. One method is using a lookup table, and the second one would be a microcontroller that is able to generate desired PWM signal at correct ranging frequencies. And finally, the main role of the inverter is to control the speed of the linear induction motor by varying the frequency and voltage inputs. So far, the team is in the simulation phases to test and compare various transistors like bipolar transistors, field effector transistors, and insulated gate bipolar transistors, and choose the most suitable one for our system. We're also using MATLAB Simulink to test the three-phase response, as could be seen in the image right here. It's a simple inverting system, and it consists of a PWM generator, a universal bridge containing the switching circuitry of the transistors, the voltage source, LNC filters to cut or pass specific frequency bands of the signal, and the load. So the team is currently generating and testing a lookup table using a comparator with a triangular wave and a sine wave input to calculate the time on and off for each transistor, which will generate the desired AC output. So currently the team is testing with MOSFETs since they have high switching speeds and low conduction loss in low current conditions. And to keep the MOSFETs on at correct frequencies, the team figured out that a gate driver was needed. And the team is currently testing a one-phase inverter using the Proteus design software. And we're hoping to complete a three-phase design by the end of this month. Okay, so the current and future work. Currently we're trying to choose an appropriate microcontroller compatible with the pod communication system. We're trying to produce a PWM algorithm to operate at specified varying frequencies. We're trying to simulate and build full-scale three-phase MOSFET driver circuit, and we're hoping to acquire MOSFET and MOSFET drivers to test the three-phase inverter circuit. So some of the safety aspects of the inverter subsystem include the implementation of heat sinks and fans for the transistors since they're switching at high frequencies. And the system will be designed to withstand continuous current drawn by the load. And finally, fuses between battery and the inverter system will be implemented in case of spikes in current, where the fuses will blow to prevent further damage to the rest of the subsystem. So I'll be now passing it down to Aiden to introduce the battery subsystem.
Hello, my name's Aiden. I'm the battery lead for the team. Just a little recap on our battery system. It's designed to provide 283.8 volts DC and up to 240 amps DC for a 10-second acceleration. We're designing our own battery protection system to ensure the safe operation of these cells. For our cell chemistry, we've decided to go with lithium iron phosphate cells because they operate at a lower 3.3 volts. This reduces the chemical effect while the batteries are in storage, which improves their life. And speaking of lifespan, they can go up to 5,000 full performance charge and discharge cycles at 80% depth of discharge, which is a priority to us because we want these cells to last for future generations of the team, which will reduce costs for our team and help save the environment. Discharge is another advantage of lithium iron phosphate cells, and they have a way higher discharge than lithium ion cells. And that's important to us because we need a fast initial acceleration and where our coast doesn't need that much power. So the pulse discharge is a priority for us. Another benefit of lithium iron phosphate cells is that they perform better at higher temperatures than standard lithium ion cells. As the temperature increases, their voltage doesn't increase by too much. Another thing is that they have a reduced risk of thermal runaway because lithium iron phosphate cells don't combust. The battery casing that we chose was cylindrical 26650 casing. Because of their cylindrical shape, they are more resistant to expansion when fully charged. The casing is also larger, which gives it higher capacities and ratings, which means we need less batteries, which makes our monitoring process more simple. The specific cell we chose was the ANR 26650 MIB cells. And as you can see, their maximum pulse discharge rating is 120 amps, which is good for us. So we'll be using 6 battery packs in series with each other. 5 of these packs will be 16 cells in series by 2 cells in parallel, and the last one will be 6 in series by 2 in parallel. This will bring our total output to the required 283.8 volts and up to 240 amps. So for our battery protection system, we're using many sensors and methods of measuring the different parameters that we need to look after, including our voltage sensing and temperature measurement, PCB, which we're designing ourselves, as well as other off-the-shelf measurement systems like Hall effect sensors, fuses, and insulation monitoring devices. Since last year, we've moved past the sourcing and design phase, and now we're onto the prototyping phase. We're currently assembling our PCB so we can start testing our sensors and cells, and we're going to start one cell at a time and work our way all the way up to our 16 by 2 setup. And once we've done that, we will send our PCBs off to be assembled more quickly so that we can be ready for our flywheel test. Now I'm going to pass it off to Sergio.
Hello, everyone. My name is Sergio Monroy, and I'm the Hyperloop lead for the software team. So first off, I'm going to talk about the telemetry and controls for our Hyperloop pod. Our pod will be made up of different subsystems, and each of the subsystems will have their own individual microcontrollers, which will be connected to different sensors and actuators. The microcontrollers will be able to communicate back to our main system, which is the pod computer, through an Ethernet TCP connection. The pod computer will take decisions based on the telemetry data it receives, and it will send back commands to the microcontrollers to take the adequate action at that time. And to introduce a little bit more about our software system, we created our software system called OpenLink last year. OpenLink was a software solution to control and monitor all of the subsystems in the Hyperloop pod. We made this an open source project, which means that anyone with interest on the Hyperloop pod can view and submit pull requests. We're going to be monitoring all of these pull requests to ensure that any contributions are useful, safe, and fit. To get a better understanding of our design concept, we have 3 main components in OpenLink. The first component is the embedded component, which is made up of all the microcontrollers used on our subsystems. This will all be connected to the different sensors and actuators, and they will be communicating back to a network switch through an Ethernet TCP connection. The Ethernet switch will then communicate onto the pod computer, which is our second main component. The pod computer will be receiving all the telemetry data and sending the commands back to the microcontrollers to take adequate action. And this pod computer will also have Wi-Fi capabilities. This way, we'll be able to remote to it from a remote client and be able to view all of the different, monitor all of the different systems and take adequate action. To To get a better understanding as to how the open link is meant to be operated by different users, I have added a use case diagram, which can be seen on the left side. This diagram shows how different users would interact with our software. The software team members will have the capabilities of adding and removing devices, as well as exporting data. The administrator members will have the capabilities of observing the telemetry data, as well as manage all of the user accounts. We will also have the mission control members, which will have the capabilities of starting and stopping the pod, as well as being able to monitor all of the subsystems in real time, so that in the event of an emergency, they're able to stop the pod. And lastly, we have the pod computer itself, which is a key component of our system, since it'll be the one retrieving all of the telemetry data, as well as run algorithms that would ensure that the pod is stopped in the event of an emergency. So last year, a lot of work was done by the software team in order to complete the setup of the Git repositories for the OpenLink pod and the OpenLink remote client. The operating systems for both the pod and the remote client are mostly complete with only minor tweaks that are needed. The main focus of the software team this year is to be able to set up the Ethernet and Wi-Fi communications for all of the different systems, and to work with all of the different subsystems teams, so that we can select an adequate microcontroller and we can program it according to what is expected of each different subsystem. This year, we're hoping to be testing our software system using the flywheel. And lastly, I'm just going to pass it back to Yamini so she can finish up the presentation.
Absolutely. So thanks so much for listening. So that was a great overview of our electrical system, as well as the way that it interacts with the software that we've decided on. And we will be using the flywheel as our testing mechanism for the electrical subsystems this year. If you have any further questions, feel free to ask them. And this is some of our contact information if you want to reach out to us about our design or any thoughts that you might have on it.
Thanks, guys. I like that a lot of team members were here to present. That's kind of fun. Usually there's just one or two, but the more the merrier, I say. So that's good. Yeah, any questions from anybody at all?
Yeah, I actually have a question.
Sure.
I was curious on the battery choice using lithium iron phosphate over newer technologies like lithium polymer or lithium ion. Just they're significantly heavier, so sometimes they don't make sense to use when just to make up for the higher power.
That's an interesting thing that you mentioned there. I haven't made any adjustments to our initial design choice, so there is a chance that we could look into other cells. We haven't actually ordered the cells yet, so it would be interesting to look into that option and perhaps ordering that as well, giving those a shot. But I personally haven't done too much looking into different cell choices. This was designed before I was the lead, so I haven't looked into modifying the design quite yet.
Okay, yeah, that makes sense. Thanks.